I also tried to choose a title that would fit in, but I added a subtle clue of what I'm interested in. Yes. All right. So how does someone who cares about social network come to think about sports? A couple of years ago, led by Hagen Wesche, who's a sports scientist, we wrote a paper that surveyed the use of network analysis in the sports domain. And part of that systematic review was that we came up with this typology of what kinds of network studies are present in sports. And some of them are the usual social network studies you would expect, interorganizational networks, networks between individuals like coaches and athletes. So this is just a different setting, but the same kind of networks that are being analyzed. Whereas the last two, competition networks and interaction networks, are very specific to sports. Right? We have these games that take place, if they're team sports, then there's interactions between the players within the team, but also usually sports is competition, so there's interactions between those different groups. And the result, if it's in an organized competition, is relevant for ranking teams, for setting up a table, and so on. So these kinds of networks, many of the rankings use network methods, are of interest too. And I left out one type of network that is very relevant inside of games, state transition networks, just because they're not social, right? But those of you who have a background in physics or computer science will be very familiar with state transition systems as well. And I, by now, consider football to me to be our model system, where many of those things, the collective behaviors that we're trying to study, are happening within constrained settings where the forms of interactions are limited, where we have a clue of what the interest is that the agents have, where we know that they have individual differences because they're different, prepared in different ways, because they have different athletic conditions, and we have a theory of what their intention is and how they want to implement it. So here this takes the role of the brain, of the neuroscience, that there's maybe an underlying mechanism that has been set within the team. And yeah, we can all ask all kinds of questions there, and by now I'm actually teaching a course on soccer analytics that tries to go over all of these aspects using football as the model system. So just a quick check, who's familiar with these kinds of dashboards? Not so many, okay. So this is a match from this weekend, and a lot of data is being collected about it and then put into graphical form to indicate how this match panned out, right? What the teams did, what has been observed, where they moved, what the individual contributions have been, what the goal scoring opportunities and the actual goals that were scored have been. Right, so this is the kind of setting, the kind of things that make someone who is interested in visualization, in algorithm, and network very, very excited, right? Because we can do all of this in a single context. But of course, there's also the historical aspect of it. And the question I want to address today is just one that will turn out to be very fundamental to address different questions in the game. And that's the question of formation, positions of players in the game. So what you see here is from the program of a very important match that was played. So we think of football as the English game, but that's only because in the 19th century, the rules that we play by today have been started. Versions of football have been common all over the world, really. This is Italy, Florence, to be exact. And on the occasion of an important wedding, there was a game that was staged for the entertainment of the public. Right? And here in the program, we see a depiction. The program contains greetings from luminaries. It contains a reprint of a 100-year-old discourse on football and a redrawing of this picture that shows the kind of game that was played. So the role of the goals are here the tens. This is really more of a battlefield than a football game. This is also where a lot of the language is coming from, that we're staging and acting a battle. And battle formations end up being players, the ones trying to move the ball into the other tent, organized in very systematic ways. Right? So easily recognizable. The next page is actually the lineup. Right? So we have the individuals that you just saw now instead of vertically, horizontally, in those various positions in different groups, 27 players on each side. on a field that is roughly the size of a football pitch today, slightly bigger. And on this page here, we're not seeing the names of the individuals, but the position they play. Right? So these locations here that are labeled ABC and so on, they have names as tactical positions. Right? And then on the next page, the actual names of the nobility enacting these positions are listed as well. This is still very common, right? This is 19th century then. Here we have the FA Cup final of 1888, the last final that was played before the first league was founded, right? Oldest competition of the world, really the FA Cup in football today. But again, we have a goalkeeper, we have 2 backs, we have 3 halfbacks and 5 forwards. So this is the same kind of arrangement. The theory with which we go into the match, right? How we assign spatial responsibilities to the players who are then supposed to defend that space or attack the opposition space. Same today, right? This is Eintracht Frankfurt. I'm choosing this not because it's my team, but because this is what the website of the German Bundesliga is used as an example of a new feature they were proposing, namely showing, first of all, what they call the tactical lineup, right? The same kind of thing that we saw before. Now we have 3 defenders, 4 midfielders, 3 attackers, and a goalkeeper. And during the game, they would use the data that is collected about the movement of the players to show where they actually spent their time. Right? So this is the theory, the underlying intention, or at least the communicated intention. This is what happened where we have those theoretical positions and then the average position over the period of the first half. And pundits then wonder that this actual formation, where we do see players on the pitch, is almost always more compact than the tactical lineup, meaning that there is less space than is suggested by the tactical lineup. Right? Because what happens if you move, if your responsibility is somewhere here on the side, you can't go there. And you can go inside. So what's going to happen to the average location? The average location will always be closer to the center than to the side if you do anything else but stand in your line. Right? And this is on an individual basis. Teams shift left and right together, keeping their distances, but then moving their averages toward the middle in the same way. So it's really surprising that we would find these kinds of statements. If you've ever seen the Dibigo Dop game on Saturday night, where Lothar Matthäus is telling you that a team is good or bad by saying that they're compact or not compact. That's what they do. Now, if we want to approach this, and of course you're wondering where are the networks now, this is where they come. Here are 3 different situations, right? Momentary snapshots of where players are in the match. And so I colored them differently so you can distinguish them. And in tactical terms, we will probably say that this team is playing with a formation that is called a 4-1-4-1. So 4 defenders here, 1 defensive midfielder, 4 central midfielders, and 1 attacker. Right? We might call this a 4-3-3, 4 defenders, 3 midfielders, 3 attackers. And we might call this a 2-3-2-3, which is very often used while in possession of the ball. Same kind of responsibilities. But in terms of the relative distances, the proximity network that we can generate on this, they all have the same structure. Right? So they're in different positions, but in terms of relative distances between them, it's actually the same structure. Right? There's no difference. And if I just exchange them, you can see that it's like the ones in the white channels on the left and on the right. If they move up a little bit, then you get the neighboring structure as well. Right? So isn't this a better way to describe what the team is doing, or a better assumption about what their organization is? If they do a decentralized, communication poor approach, because they can't talk all the time to each other, but they use each other for orientation, they most likely are using the ones that are relatively near as the initial ones. And here, this is not a neurological theory, but here it's a tactical idea, right? This is how it's being practiced, how you orient yourselves. The four spatial references that players use are the ball, the markings, the opponent, and the teammates. And I focused only on the teammates in this example, right? Okay, so this is what the data would give us, right? From last year's Euro. We can see movement of players and the ball using tracking data as it is routinely collected in professional football by now. And if you look closely, you might see that the Swiss team has some kind of relatively static organization, even though all of the individuals are moving all of the time. Right? Now, if we introduce the structure on top of it, then we do see changes in the structure, but these changes are only in locations where there's adaptation to the opponents. Right? The opponents are moving, you have to mark them, you have to close down the space, but overall the situation remains relatively stable. Right? And now we want to use this to infer from the observations what is the role that a player is playing, for example, for position analysis or for checking whether the tactics work the way you wanted to or whether players deviated from their responsibilities. Right, so how do we construct these networks? Now it's lost. So somewhere the focus is gone. I don't know who has it. Okay, there you go. So these are Delaunay triangulations, very common form of triangulating points in the plane. The defining feature of these Delaunay triangulations is that whenever you have one triangle in there, and you can include or exclude the goalkeeper depending on your goals, but if you have a triangle like this one, then the circumcircle of this triangle will not contain another point. Right? They have very interesting features. They contain the convex hull, the nearest neighbors, all of these things that are geometrically relevant and important. They maximize the minimum angle that is there, so we don't have the skinny triangles. So they seem to be a good representation of what spatial proximity can be and who might be relevant for who. There's one downside, and that is if we have these triangles, then the circumcircle of any of the edges in there need not be empty. Right? If it is empty, then of course any such triangle will also be empty, that's fine. But this graph here may contain a point. Now if we move this to the red point, then by definition the blue point will be outside. Right? In the same way, if we add the blue circle, it'll be empty as well, right, for those 3 points. But both of these circles are very close to each other. And if I move one of the points inside of the other circle, the diagonal is going to flip. Right? So this black edge here will become the edge in there. And the decision point is when all 4 points are on the same circle. Right? This is when we're not really sure. When there's a degenerate situation, we're not sure who is using who as a reference. There might be one edge or the other, and we don't want these kinds of ambiguities. So what we do is we look at the distance between those two circumcenters, and if they're far away from each other, we're fine, then the situation is stable. If they're close to each other, then we're close to flipping the diagonal, and then we just drop both of the edges, right? And instead just maintain the circle of the 4 points. Because this is then scale dependent, we cannot look at the distance between the two, but we look at the angle between the two. Right? This is what is called a stable Delaunay triangulation. They have the downside that it can be very sparse. So what we do is we remove iteratively those edges that are the least stable and then continue doing so, updating the angles around the others to obtain something that is relatively stable and still very well connected. That requires a few adjustments on the outer face and on those faces that are no longer triangles, but that can all be worked out. And then there's a simple algorithm that does nothing but computing Delaunay triangulation and removing in a priority queue the edges that are the least stable. I'm just showing this to show its simplicity and that you can actually do this in real time. Right? If we only have like 10 players in a team, maybe we're looking at the joint representation of both of them. If we have 25 frames per second, that can all be done live. All right. How does it differ from the Delaunay triangulation itself? Well, most of the time they have changes. One changes when the other changes as well. Sometimes, very rarely, both of them change between two frames. If one changes, the other does not, and vice versa, which means that we're capturing different moments for change, the moments where maybe something becomes relevant rather than being indeterminate. Right? That seems like a better moment. And here, if we choose our angle, at what angle, what is our sensitivity, and we see that it's relatively stable, how many changes we have, and we choose 45 degrees for other geometric reasons I'm not going to go into here. Right. So if we do this, then over time, we have one shape graph, as we call them, for every frame. We can aggregate across the frames. So at the end of the half, for instance, instead of showing average positions, we can show what is the typical structure that we're seeing there. If for at least 1/3 of the frames an edge is there, we show it here, and the ones that are more frequent are thicker, and the ones that are less frequent are gray. And these are the average positions of the nodes. So this is the structure on top of what the average positions are. And you notice that those two defensive midfielders here are almost in the same position on average. If I move them apart a little bit, like here, then you can see that this one here is the more defensive one, staying closer to the other two. This one is the more attacking one, so they divide up the space in the middle between them, something that we can't see from the average positions, but we can see from the structure. And for the other team, in this one match, it looks like their midfielders and attackers are all very crowded in the center, and this is the prime case of where the average positions are misleading, because here we have lots of crisscrossing edges. Right? If you've seen the Delaunay triangulation before, they are all planar. There are no crossings. These crossings are in separate moments in time. Right? So players are switching sides left and right before they go into a different place. And that's maybe more obvious if we move them apart in this way. Now, quickly recap, we have a moment, right? One frame, 25 of them per second, players are in some place. We construct a shape graph that is not a triangulation, but may have these larger areas where it's almost circular, and we can't really say who is referencing who most of the time. To determine who is the defender and who is an attacker, we do a two-step process. We look at the centers of those faces, cut off the ones that are below the lowest center, above the highest center. These are the defenders and attackers, because we are in an oriented space, right? It's not just a Delaunay triangulation in the plane, but the plane is oriented towards the other goal. And then we can distinguish the ones in between those two lines into defensive midfielders, central midfielders, and attacking midfielders, using other rules on the structure of the graph that, I'm not going into. Right? This gives us a vertical division. We can do the same thing horizontally, which gives us 5 ordinal levels, independent of where on the pitch it are, only about the relative positions between the players. And these are standard denominations of players like a right back, a center back, a central midfielder, center forward, and so on, that are now inferred from the momentary structure, but can change over time. Right? Every 40 milliseconds, that can change because players are moving. So we map this out over time. Right? And this is every moment in time. Defensive midfielder, because it's light blue, mostly on the left side, because it's brown. If it's green, it's on the right. But since it's all light colors, this is a defensive midfielder staying mostly in the center of the pitch. At halftime, substituted, the one that's coming in is playing in a more attacking role. Right? And we can see this immediately. And now we can put this together for the entire team and say that, oh, well, this team seems to have had 4 defenders, 2 central defenders, 1 on the right, 1 on the left. 4 midfielders, 2 defensive ones, 2 more attacking ones on the wide sides, and then 2 center forwards, left and right. They are exchanging sides very often because green and brown are switching in the lower part. So the thing that we just observed for the aggregate structures, we can now see laid out over time. We can also see that there are big changes in the structure at some moment. For instance, player 27 is substituted for player 34, and the player coming in is not at all playing in the same role. So this player is moving somewhere else, and because of this, another player is moving into a different space. So we see this more clearly in the other team here, or if I go back to the match that we just saw. More recent from the past Euros. These are the 2 teams. Let's say we focus on the German team because there it's very clear. So when Andrich is substituted for Bayer, this is a defensive midfielder who's playing mostly in the center. After the substitution, the incoming player is playing in an attacking role in the center. And because of this, to compensate for it, we see at the top that player 21, which must be Gündoğan, is moving from this advanced role into a lower role. So a switch between the team. This helps in opposition analysis and analyzing the game and so on. And there's lots more details we can observe here, but I spare you those. And just conclude by saying that this way of representing collective movement to me is like a basic data structure. Now we express the shape of the team. We can read from this shape what the positions of the players are. We can use those positions of the players to infer what the formation is that they play, because of those 21 positions that we had there, only 10 can be enacted, and depending on which ones it is, we have a 3-4-3 or some 4-4-2 or whatever other formation. All of these things can be done on top of the instantaneous representation of the relative division of space. And as I said, thinking of this as a model system, we can also apply this in other contexts where we want to infer, like the inverse problem of detecting what is the strategy that this group is trying to implement. Thank you very much.
Thank you very much.